Hi guys, a very good morning and a very happy Pongal to all of you, right? So I know that we are having class on a weekday. Sorry, a holiday, right? That's okay, right? It's just 1 hour, right? I'll not trouble you much today, right? So we'll just wait for 2 more minutes. Let your friends join, right? So all of you did shopping, bought new clothes for Pongal. Hmm? Especially girls. Divya, did you buy anything? What happened? So silent. Hello.
Sir, your voice is breaking for me, sir. Can you just repeat?
So I was asking. So I was telling happy Pongal to all of you. So I asked you whether you bought your clothes, new clothes, all that.
Yes, sir. Last month itself I bought, sir.
See, that's the point. Good, good, good. Very nice. What about the other two, Mithil and Rohan? Did you buy clothes?
Yesterday event, sir.
See, that's the difference between guys and girls, right? Oh God, generations after generations, right? Things won't change. Nice, nice. 7-5, and it's still only three of you. Hmm. 1 more. Okay, guys, I think we'll start right away. Right. Okay. So, guys, we have completed isomerism as I told you, right? So we saw uh, optical isom. Sorry, I told you that. Say where was this? I think so. So yeah, so I told you that stereoisomerism can itself be divided broadly into constitutional and conformational. And constitutional, basically, we are going to do it on paper, and conformational is going to come out because of CC single bond rotations, right? And we saw a little extra stuff, but this is the only thing which is there for you, right? Ethane, right? The projections, right? The eclipse structures, staggered structures, and little bit more if you go. If you take butane, you will extra be getting skew or gauss structures also, right? And along with obviously like eclipse and staggered, right? And then this we saw, right? I told you that cyclohexane is pretty, what to say, special, right? So what I told you is there will be something called as angle strain in all these cyclic compounds because the bond angle is no way close to the tetrahedral angle, which is 109 degree 5 minutes, right? So, but cyclohexane has almost has the bond angle to be equal to the tetrahedral bond angle, but still, this is not going to be the shape of cyclohexane you see in reality. I told you that these four are the ways in which you will actually see cyclohexane, right? So I told you this is how the chair looks, right? So these are different conformations of cyclohexane. So if at all we complete our syllabus and we have time, we can look into it. There are a lot of good crazy stuffs we can do in this, right? Fine. Anyways, so that's about your isomerism. Then I told you that we are going to see about these intermediates, right? Now this is the flow chart of any organic reaction. So we have something called as reagents. Substrates can be anything, any functional group you can have, and they both would react together to form unstable species called as intermediates, right? And eventually they will lose something or gain something to form the eventual products, right? And for us to understand what is that intermediates, we have to understand how a bond breaks in organic chemistry, right? Now I told you bond fission or bond breaking is same, right? So this can be of two types. One is what is called as homolytic bond fission. The other one is what is called as heterolytic bond fission, right? So when you have, for example, a CC single bond like this, I mean a CC bond like this, right? So I know for each bond, two electrons are shared, right? So if if we are going to break the bond homolytically, what do you mean by that? Means wherever the electron came from, right, it is going to go to its parent atom, in the sense that you see that there are two electrons shared here, right? Shared here, you can see that, right? So you're going to break the bond in such a way that these two electrons are going to go to their parent carbon atoms. Basically, this electron to this atom, so this carbon atom, and this electron to this carbon atom, right? So I told you, you will be ending up with a single unpaired electron on the carbon, each of the carbon atoms, right? So whenever you have single unpaired electron, which is not a bond pair, which is not a lone pair, a single electron which is not paired, those are what are called as free radicals. Okay, so what you have to understand is whenever homolytic cleavage happens or whenever homolytic bond fission happens, the intermediate formed is actually going to be a free radical, right? Okay, and I hope you there is a different way of arrow, there is a different kind of arrows we use for homolytic bond fission. So these, you can see the arrows here, isn't it? So these are what are called as half arrows, right? So whenever you want to specify that it is going to be a homolytic bond fission, this is how you have to represent it, with the half arrow, this side and that side, right? Okay, any questions guys till now from yesterday's class? Okay, so I suppose there are no questions, right? Fine, we'll move on. We'll move on to see what is this heterolytic bond fission. Okay, right? Fine. So in case of, oh, sorry. Okay, in case of heterolytic bond fission, we'll see what is going to happen, right? Say for example, right, I have CH3 Cl. Okay, I have, for example, say CH3 Cl. Okay, now obviously what you see is I have a CCl bond and there are three hydrogen atoms attached to this carbon atom. Okay, right. Now, in case of heterolytic cleavage, unlike in homolytic cleavage, what happened? Wherever the electrons came from, they are going to go back to their original positions, in the sense that whichever atom it came from, it is going to go to that particular atom. Right. Now here also you see there are two electrons shared here also. Right. Right, there are two electrons shared here also, but in this case I am going to make sure that the two electrons which are shared are going to go to one of the species, right? Now unlike there, one electron goes to one, another electron goes to another, but no, here both these electrons are going to go to one of the atoms, right? Now which atom it will go is the next question, right? So either you can put it in the carbon atom or say you can put it in the chlorine atom, right? Okay, now that will be decided by dash. What? That will be decided by
Electronegativity, sir.
absolutely right. It is going to be decided by the electronegativity. The more electronegative atom will take up the electron, the lesser electronegative atom will lose the electron. Right. So obviously chlorine is the one which is going to take up the electron. right? Now, how do you represent it? This is how you represent people. So you are going to break this bond, making sure that the chlorine atom gets the 2 electrons. So this is how a full arrow, right, indicating that these 2 electrons are going to go to chlorine, right? Okay, fine. Now the products are pretty simple here, isn't it? So obviously I'll be getting a Cl minus, that's for sure, because chlorine has now got an extra electron in the sense the electron which it should have had before the bond has formed, that is this electron, right? And an extra electron from the carbon also, right? So definitely here I'll be getting Cl minus, no doubt, right? And what about the other thing left? That is the CH3. This, when you just write CH3, now this carbon has lost an electron. Is it not? This carbon has lost an electron. So obviously this is going to be a positive charge. Okay. So guys, this is what I want to tell you. Whenever you see carbon atoms having positive charges, right? So those are what are called as carbocations, right? Those are what are called as carbocations whenever you see carbon having a positive charge, right? So whenever a heterolytic cleavage happens, and in that process, if carbon possesses a positive charge, those are what are called as carbocations. Okay, right, fine. So let me now, okay, so we will just list one more intermediate. The first intermediate listed was free radicals. The second one is this carbocations. Okay, right? So till now you have two intermediates, free radicals and carbocations. Okay, fine. Now in the heterolytic cleavage, this time you gave the carbon, you gave the electron to the other atom, and the carbon has lost electron. Now there can be a case where carbon has gained electrons also, right? We have already seen one example, people. Can you tell me what is that? Carbon gaining electrons. What was that? Where was it? Just think and tell me. Where was it? No, we actually saw it when we saw certain stuffs. Where did we see it? Hmm? Where did you see it? Let me see if anybody remembers. It's pretty easy, right? So basically, I'm telling you that I'm going to have carbon to have a negative charge. Where did you see it? Okay, I'll give you a clue. It's somewhere in isomerism. Okay, it's somewhere in structural isomerism. Still no. Oh, is there something in the chat? I don't think so, right? Yeah, no, nothing in the chat.
Is it related to resonance?
So, yes, it's about automerism. Absolutely, yes. Right. So what happened there? So what happened there is when I had, say, for example, a simple aldehyde or a ketone. Right, this is an aldehyde, for example. I know that this hydrogens are acidic. Alpha hydrogen, this is the alpha position, right? And that hydrogens are acidic. So what happened there? You saw if I write it as CH2H and CHO, right? What you saw there? This hydrogen came out as H plus. Means what? There are 2 electrons shared here, right? And I'm going to make a heterolytic cleavage such that these 2 electrons are going to go to carbon, and only then this can come out as H plus. Right, this can come out as H plus. So what will be remaining after this? If I remove the H plus, you will be remaining with CH2 minus CHO. This we saw, right? In tautomerism, obviously, this will go here and then C double bond O breaks and then tautomerism happens. And that one we saw. But what you have to understand is here you see the carbon atom is possessing a negative charge. Okay, so in general, if I want to represent it in a simple way, right? Say if I have carbon atom with 3 other groups, say there is some other group Z. Okay, so it can be hydrogen, it can be anything, right? Say now I'm going to break this bond again. You have 2 electrons shared here. I am going to break this bond in such a way that the carbon is going to gain electron and this is going to come out as a positive charge, right? So how do I represent it? I have to represent it like this. Now put the arrow mark towards carbon atom, full arrow towards carbon atom, right? So what will you end up with is C with 3 bonds with a negative charge plus a positive charge on Z, right? So this, whenever you see carbon atom possessing a negative charge, those are what are called as carbanions. Pretty simple. The name and terminology is pretty simple. Positive charge, carbocations, negative charge, carbanions. So these, the third one, that is, where is it? Oh, yeah. So the third intermediate possible in your organic chemistry is carbanions, right? The third intermediate possible is carbanions. So I would say these 3 are the primary intermediates, right? But if you go to higher levels of chemistry, there are something called as carbenes, nitrines, ketenes, so many stuffs are there. Yeah, imines, like we don't have to go into that, right? But primarily, you will see these 3 in the 90% of the reactions. 90% of organic reactions, right? Free radicals are yeah.
So carbocations and carboanions are formed from heterolytic fission.
Exactly. So when I have homolytic cleavage, the only possibility is free radicals. But when I have heterolytic cleavage, depending on how you break the bond, I can either end up with carbocations or end up with carbanions, right? But that also will be able to easily predict, is it not? If you see that the carbon atoms attached to a highly electronegative element, at that time, definitely carbon atom will possess the positive charge, right? And opposite way, and if you see that it is attached to a lesser electronegative, say an electropositive element, then carbon atom would have had a negative charge. Okay, right? But again, carbanions are pretty, what to say, compared to the reactions where carbocations are produced, not much in case of carbanions. Yeah, there are reactions, right? But free radicals and carbocations are majority. Carbanions compared to these 2 are less, right? Okay. But the only problem with NCRT is they will teach you organic chemistry in the way it should not be taught. It's absolute crap, guys. Like unless and until I studied organic chemistry by myself for my teaching purposes, I really didn't understand this particular thing, right? So I'll tell you what is wrong with NCRT, right? So you must have seen like you will see more like now you have more of physical chapters, physical chemistry chapters in 11th. Now if you go to 12th, majority will be organic chapters, right? So what happens there is like here as well as there. So you will just, they'll give you the reaction, right? They'll give you reaction, they'll give you the reactants, products, catalyst, temperature, all these stuff they'll give you for every reaction, right? But what will they not give you is the mechanism. Mechanism is the flow chart which I gave you, right? Reagents, substrates, intermediates. I don't think for, I would say for 99% of reactions in your textbook, right? They wouldn't have given mechanisms, right? And I really don't know how am I going to teach you if that's the case, right? But guys, I think I will follow my style. Okay, so because there are certain things has to be done in the way it has to be done, right? So I am not diluting anything. Like I am teaching you science, I am not teaching you for marks, right? I have some knowledge and I would love to share it with you, and that's the motto, right? So even though it is going to take some time, right, I will tell you what exactly happening is, like what exactly is happening inside the reaction, right? I'll give you a microscopic view. I'll just take you inside the reaction, right? And I'll show you what exactly is happening. Almost reactions what we see. Okay, right? Fine. So we'll move on. So what I was telling, yes, as the question is, yeah, heterolytic cleavage will always end up with carbocations or carbanions. Okay, fine. Now, so these are the intermediates. Okay, now I want to stress upon certain points, people, right? So I want to talk about the hybridizations of all these 3 species, right? So when I have a free radical, what is the hybridization of carbon? When I have a when I have a carbocation, carbanion, what are the hybridizations there? Because that will be really helpful. Okay, say let me take a carbocation. I mean, say free radical I take normal, say CH3 dot. Okay, so this is what is called as your methyl free radical. Okay, so let me compare it with say CH3 plus, right, and say CH3 minus. Okay, this is neutral species. Please remember, if they ask you is our free radical charged, no, they are neutral, right? They are just have a single unpaired electron. Okay, right. So now this is a positive charge and this is a negative charge. That is straightforward, right? So I want to know what is the hybridization of all these three. That's what I need to know, right? So it's pretty easy, right? Can you guess, guy? Okay, first come back to this thing later. At least for this, you can predict the hybridization, right? For CH3 plus, for carbocations, you can easily predict the hybridization. Can you tell me what is that? I told you how
What
to
is the
find
question?
what is the hybridization of this carbon in carbocation.
3, sir. SP2.
Yes, it is sp2. Okay, so it's pretty straightforward, right? So I told you steric number is equal to number of atoms bonded to the central atom plus number of lone pairs on the central atom. Okay, so in this case, what do you see? The number of atoms bonded to this carbon is 3. There are 3 hydrogen atoms. Okay, fine, right? And yeah, there are no lone pairs, right? Obviously, right? Obviously, how do you count the lone pairs? Carbon had 4 valence electrons, right? So out of that, 1 has gone because of the positive charge. So how many is remaining? 3 is remaining. So all the 3 are involving and bonding with hydrogen, right? So there are no lone pairs, right? So 3 is a steric number. So obviously, it is going to be sp2 hybridized, right? So let us come to carbanion, right? Can you guess what is the hybridization? Yes, any guesses?
Will be SP3, sir.
Yes, it is sp3, right? So how do you find it? So first, let me, okay, obviously there are 3 bonding atoms, no issues. 3 hydrogen atoms are there, but carbon, if you see, there are 4 valence electrons already. Right now, you have 1 more electron coming in the form of a negative charge. So totally, I have 5 valence electrons. Okay, so out of these 5 valence electrons, 3 are involving in bonding with 3 hydrogen atoms, right? So obviously, there are 2 more electrons left out, right? So 2 more electrons means 1 lone pair, making it 4 sp3 hybridized. Again, I repeat, right? So you have 4 valence electrons in carbon, right? And 1 comes from the negative charge, one more electron comes from the negative charge. But totally now I have 5 valence electrons in carbon, in this case, in the carbanion case, right? So out of these 5, 3 are involving in bonding, right? 3 are involving in bonding, right? So obviously, if 3 are involving in bonding, 2 more electrons are just there. That means there is 1 lone pair. So making it the steric number 4 and giving the hybridization to be sp3 hybridized, right? So always carbocations are sp2 hybridized and carbanions are sp3 hybridized. Okay, now coming to free radicals. Okay, any guesses what hybridization it would be? Yes, do not wait. If you know the answer, do not wait for someone else to give the answer. If you know the answer straight away, please give it.
Sir, could you repeat the question?
Same thing. What is the hybridization of this carbon in free radicals?
SP2, sir.
Yes, it is sp2. Okay, now this will be little kind of tricky, right? Fine. So anyways, how do you find it? So obviously there are 3 hydrogen atoms. Okay, now I have to check for lone pairs on carbon, whether it's there or not. Okay, so see guys, I have 4 electrons in the valence shell and this is neutral, right? Now out of these 4 electrons, 3 are involving in bonding and there is 1 electron left. Can I consider this a lone pair? Absolutely not. This is not a lone pair. This is one single electron. Correct. So I cannot consider as a lone pair. So just there are 3 bonding atoms and no lone pair. Again, making it sp2 hybridized. Right, again making it sp2 hybridized. So free radical and carbocations are sp2 hybridized, whereas carbanions are sp3 hybridized. Okay, now why I told you this is like when I look at certain things, it will be very helpful. You'll understand why I told this when I just continue. Okay, fine. So you have to remember this, people. Right, carbocations and free radicals have sp2 hybridization, and carbanions alone has gonna have sp3 hybridization. Okay, right? So I hope everybody understood how is it sp2, sp2, and sp3, right? Okay, now what I have to tell you is, people, right? Now any intermediate, all of these 3 in carbocations, carbanions, free radicals, all of these, right? And I just say intermediates in general, okay? Not all intermediates, especially these 3, right? Can actually be of 3 types. Okay, what are they? If you ask me, first one is what is called as a primary intermediate, secondary intermediate, and tertiary intermediate. Okay, so if this is primary, I'm not writing the full this things. This is secondary. This is tertiary intermediate. 3 degree means tertiary. 2nd degree means secondary. 1 degree means primary. Okay, now what are all these things? Right. So it's pretty simple. So in case if I take primary, guys, right, now what you have to understand is the carbon possessing the radical, or say the carbon possessing the positive charge, or say the carbon possessing the negative charge is attached to one other carbon atom. Say for example, this is an example for primary. Now, how did I say it? This is the carbon atom possessing the positive charge. It is attached to how many carbon atoms? It is just attached to only one carbon atom. So this is called as a primary carbocation specifically. And these are intermediates. In general, if it's a positive charge, I can say that is going to be a primary carbocation. How is it primary? I told you, you just have to look at the carbon atom possessing the charge, or say the radical. You have to look at how many other carbon atoms to which it is attached, right? Okay, so obviously in this case you see that this carbon atom is having the positive charge. It is attached to only one carbon atom, so I am going to call it as primary. Okay, so if I draw this structural again, say I have a cyclic structure, and this, say there is a methyl group, and here I'm going to have a positive charge, for example, right? So you see this is the carbon atom having the positive charge, and it is attached to how many other carbon atom? Obviously only one other carbon atom. So again, this is primary carbocation. Again, this can be a negative charge, or say it can be a radical, can be anything. Say if you put a negative charge, it is going to become a primary carbanion. Right. Now, obviously, I think you'll be able to guess what will be secondary and tertiary, respectively. Right. So secondary, obviously, you see that if the carbon atom having the charge or the radical is attached to 2 other carbon atoms. Right. So how do you say? For example, I say I have CH3, CH dot. Yeah.
Sir.
Yeah.
Sir, in third tertiary, how much will it have, sir?
Coming. Secondary is 2, tertiary will have 3. That's it.
No, sir. How will it affect that equation, sir? CH3, CH2I.
CH3, CH2I.
No, sir. How will it affect that equation, sir? The third one.
What equation?
CH3, CH2.
This is not an equation. This is a carbocation, right? This is just a
Yes, sir,
carbocation.
that only, sir. That only I set it as the equation.
Okay. See. Okay. So in this case, it's primary. Why is it primary? Carbon having the positive charge. I told you, carbon possessing the charge attached to how many carbon atoms? How many other carbon atoms? Do you see only one carbon atom, isn't it? Right? So that is going to be primary. Now, in this case, what do you see? Say this is also example for primary. In this case, what do you see? This is the carbon atom having the radical, right? Now you see it is attached to two other carbon atoms, right? So this is called to me secondary radical. I call it secondary free radical or secondary radical is what I'm going to call it, right? Say another, like if you want a cyclic structure example, I can give you this, right? Say I put a negative charge here, or say a positive charge here, something I put. Right now, what do you see? This is the carbon atom having the positive charge. Now, where do you see how many carbon atoms? One, two. Two other carbon atoms it is attached to. So again, this is going to be a secondary carbocation. Okay, right. Now, I think last one you can easily guess how many carbon atoms are getting attached. I think it was Mithun who asked the question, right? So I think obviously it's going to be three. Let me give you an example. So when I go for tertiary stuffs, right? So tertiary will be now the carbon atom which is having the charge is going to be attached to three other carbon atoms. Pretty simple, right? Say now if I have say CH3, C plus CH3 and say one more CH3 here, right? What do you see? This carbon atom having the positive charge is attached to three other carbon atoms, making it a tertiary carbocation, right? Say I can have a cyclohexane, a methyl group, and this carbon, say if it is gonna have a radical, or say I put a radical here in this carbon, right? Now this is the carbon atom having the radical. So how many other carbon atoms attached? First carbon atom, second carbon atom, third carbon atom. Again, making it tertiary. Yes, understood, Mithun? It was Mithun only, I suppose, who asked that question.
Yes, sir.
Right?
Actually, I'm not
Okay.
able to on my microphone so fast, sir. So I'm getting delayed to on my microphone. If I
No
on it
issues.
now, it is
No
getting
issues.
on after 5 seconds. So that's really the problem. Yes, sir.
Okay. No issues. Anyways, you understood, right?
Yes, sir.
Okay. Very good. Right. So yeah, so hope you understand what I mean by primary, secondary, and tertiary intermediates. Right. Now, what will I call this when I just have a CH3 and say a dot or a plus or a minus? This is not a primary, this is not secondary, this is not tertiary, because there is no other carbon atom. All three are hydrogen atoms. Right. So this is generally going to be called as methyl intermediate. So intermediate again can be anything. In this case, it's going to be a methyl free radical, or if it is a positive charge, methyl carbocation, negative charge, methyl carbanion. Okay, so I would say four types are there: primary, secondary, tertiary, and methyl. Actually, there are so many other stuff, right? But for your level, this is enough. Okay, right? So primary, secondary, and tertiary. That's enough, and methyl, obviously. Okay, right. Now, guys, you should have seen this reaction. I like what is see why are we studying all this, right? This is the core of organic chemistry. This is the backbone of organic chemistry, right? Now, how will I put it to you? I have to take a reaction which you already know, right? So let me take this reaction. I have, say, for example, CH. This is an alkene, correct? Right. So when I put HBr to this, right? So these are what are called as addition reactions, right? We'll come back to this later. Do not worry. I'm just giving you I just want to, I want you to understand how important all these intermediates are. That's what I'm trying to tell you. Okay, right. So when I put HBr, people, okay, so you will see that, see now what will you have? There can be two products, right? What can be two products? Now, depending on where the hydrogen atom and the Br atom gets attached, I can have two products, isn't it? Say Br atom has two possibilities, either to this carbon atom or to this carbon atom. Obviously, again, hydrogen atom can be here or here, right? I can have two possibilities, correct? So how will a first possibility is, say second carbon atom, I'll have the Br. One second, guys. So, oh, sorry. Right. So I'm telling I'm going to have the Br here, right? And obviously the third carbon atom is going to get the hydrogen. This is one of the products, right? Now the other product is say CH3, CH2, that is the second carbon atom has now got the hydrogen, right? So now I'm going to have CH2 and Br. These two are the possibilities I can get, right? Now you must have seen this, guys. Which do you think will be in major amount? Obviously one of them will be say 80%, another will be 20%, or say 70%, 30%. But what you have to understand is one thing is going to be a major product, another one is going to be a minor product. Okay, now tell me, if I just put it as 1 and 2, I think you must have studied this. Which is the major product? No, I'm asking you just because your school has completed hydrocarbons. That's why I'm asking you, right? So yeah, tell me, what is the major? What do you think is the major product? It can be you if you don't, even if you don't remember. Chuma, it's a guess. I think everybody can participate here, right? So look at the structure. I'm sorry. Look at these two structures, right? And what do you think? Which one is going to be the major product? You can put it in the chat box, and you can unmute yourself and speak also. Yes, go for it. It's just a guess game, people. Don't be shy. Please go for it. Yeah. Which is the major product? Okay,
So
so two. Okay, so 1 vote for 2.
So
yeah.
2, sir.
Okay, so again 2 votes for 2. We have 3 more people. Quick, guys. Oh, okay, I have, only 2 of you. Okay, so Divya, Mithun, what do you think? Okay, so I suppose they have some problem. Okay, so guys, for us to understand all this, right, you really have to understand what is the mechanism of this reaction, right? So you are seeing this is how NCERT will give you. They will just give you the product. I mean, they'll just give you the reactants. They'll give you the product, and they will tell, this is the major product and this is the minor product. And I don't know whether you have seen this. There is something called as Markov-Nikov's rule. Did they mention this in hydrocarbons?
Yes, sir, they mentioned so.
Okay, they have mentioned this, right? So anyways, according to Markov-Nikov's rule, this would have been the major product. But don't worry at all. Don't worry. I am not going to the detail. Like I'm not, I'm not going to the reactions part right now. But all I wanted to understand is the importance of the intermediates. Okay, so I don't even have to know this rule. I don't care about these rules and all. Right? Why I don't care about the rules is because I know what is happening inside this reaction. Okay, right. So anyways, right. So guys, let me tell you what exactly is happening inside this reaction. Okay, so these are what are called as these kind of reaction, addition reaction. Whenever you have an alkene and when you add something to this, right? So those are what are called as, especially they are called as electrophilic addition reactions. Okay, so let me mention it somewhere, right? It's called electrophilic addition reactions. Okay, now I have to tell you what do you mean by an electrophile, right? First you have to know what do you mean by an electrophile. An electrophile, electro is electron, phile means loving, right? So electrophiles are electron loving species, or in other words, I can say that they are negative charge loving species. So what are they now? What kind of charge they will be then? If they are negative charge loving species, what kind of species are they? One positive or negative?
Positive.
Obviously, right? Opposite charges attract, right? So these are basically going to be positive charges. This is how I represent an electrophile, E plus, right? But again, it need not be always what is that? A positive charge. It can be also neutral, right? So all you have to understand is it should have some affinity for electrons. Say any Lewis acid can be an example. BH3 is a good example because this is a Lewis acid, because this can still accept 2 more electrons. Boron can accept still 2 more electrons. This can also accept electrons, right? So anyways, we'll not go into the details. So this reaction, what we saw here is what is called as an electrophilic addition reaction, right? So what happens in these kind of reactions is, now let me give you a general picture, then we'll go for the case which we took, right? So when you have a C double bond C, right? So when you have a C double bond C, and say I go for HBr, for example, okay? So what happens is, first, oh, I have 2 more bonds. First, H plus attacks from this. First, when there are 2 kinds of addition actually in organic chemistry, it's possible. One is this electrophilic addition. The other one is what is called as nucleophilic addition. Don't get scared with all the words. It's pretty simple. Nucleo means nucleus, positive charge. Phile means loving. So they are going to be exactly opposite. They're going to be negative charges, or say the species which has lone pair of electrons. So don't worry about this, right? So this is the H plus, right? Now it is going to attack the pi bond, right? I would say generally this is not how I see it. It is actually going to be the pi bond attacking the H plus. Now, why do I say it like this? Is because in general, in chemistry, like not in organic chemistry, in general chemistry itself, we see that the negative charges are the one which would be moving. The electrons are the one which would be moving. We never say protons are moving. You must have never heard about this, isn't it? So it is better to understand that the pi electrons are the one which is going to attack this H plus, right? Now, but for our understanding now, okay, so let me assume that the H plus is the one which is going to attack the double bond. Okay, now this hydrogen people has two places where it can attack. Say basically it can attack this carbon atom or this carbon atom, but in this case it's symmetrical, because as long as you know what are these 4 groups, right, you cannot tell for sure. But anyways, now I'm just giving you a general example, right? Say assume that this carbon atom has attacked, this hydrogen H plus has attacked this carbon atom, right? So obviously the pi bond will break like this. Is it not? If I break the pi bond like this, what happens? This carbon atom is the one who's going to have the negative charge, and obviously the positive charge will come and attack here, right? Now what happened to this carbon now? This pi bond is broken in this way. This carbon atom has got the negative charge, and that was attacked by H plus. So this became again neutral. But what happened to this carbon now? Tell me, what charge there will be there? Did you understand the question?
No, sir.
Okay. So, see, let me put it in a little step-by-step way, right? Okay. So I have H plus coming. This is the first step, right? Okay. Say now I'll break this bond in heterolytically. Okay. Now if I break this bond heterolytically, so this carbon will have the negative charge. No issues. If depending on how I break it, you have put the arrow mark towards this carbon atom, so the negative charge goes here. So what charge will be there on this carbon atom?
Positive, sir.
Definitely, because this has lost electron. This carbon has lost electron, and this carbon atom has gained electron. So this will be a positive charge. Okay. Now obviously the H plus will come and attack here only, right? So if that happens, you will see that C with a positive charge, right? And you see there are 2, and the hydrogen atom has attacked here. No issues. Now what do you see here? What is what is the intermediate? No, what is the intermediate called as now? Tell me. What is the intermediate here? What is the intermediate? What do you see here in this? There can be 3 intermediates. What is the intermediate here?
Still methyl intermediate, sir.
No. Just it's a carbocation, isn't it? You see carbon atom having a positive charge, right? So the intermediate in this reaction is a carbocation, right? You, by looking at this, you should not say it's a carbanion, because this is just for your understanding, right? So like actually what happens is just like this, the bond will break and simultaneously H plus will attack, right? But I now showed you as two steps, right? Okay, so anyways, this is a carbon atom having a positive charge, and this definitely is going to be called as a carbocation. And what is remaining? Remaining is my Br minus from HBr, right? Obviously, it will come and attack here, right? So now I'm going to have one Br here, and the other one had got a H. That's it. This is how the addition reaction happens. First, the H plus attacks, makes a carbocation, and then the Br minus attacks, forming a bromide. Any questions, guys? Everybody understood?
First, I have
Yes.
to sort out with the positive one. So, like plus, whichever has plus. In HBr, H had the positive. So, we took
Okay.
H first. Like that, we have to do, sir. Like always take the positive.
Yes, always. Yeah, whenever it's going to be, and whenever you see addition reactions in alkenes, it is always going to be the positive charge which always attacks first, always. Right?
Okay.
Br minus will always attack second. I mean, not Br minus, any other negative charge if you have, right, will always attack afterwards, second time. Okay,
Understood,
so
sir.
in any electrophilic addition reaction, I would say most of the electrophilic addition reaction, you will see that carbocation is the intermediate. Okay, so I hope everybody understood the mechanism. This is what is the mechanism, right? H plus first attacks, and the other carbon atom, whichever carbon atom has got the hydrogen, the next one will get the positive charge. But don't muck it up like that, right? It's pretty straightforward, right? So you break this pi bond heterolytically, you form the positive and negative charges. H plus attacks first, and then what is remaining is a carbocation, and then the Br minus attacks wherever the positive charge is there, forming the bromide. Pretty simple. What is the time? Okay, now why did I start all this is because I want you to understand, where is it? Where is the reaction? Here, right? So if you look at this reaction, you see I told you that there are going to be two products. Now, how will you tell which is the major product? Right? Now, like, let me take this example now. We'll see what happens there. So the example which I took was CH3, CH, double bond, CH2. Right. So first, H plus attacks, right? Obviously from HBr. Now this H plus now has two possibilities, isn't it? Now last time it would have, like, say what you did is you made the negative charge on this carbon. Now you could even placed it like this, right? Made the negative charge on this carbon and positive charge on this carbon. That is also a possibility, right? So this again is the same thing here. Okay, right. Now if let me actually put it in a little different way. Okay, right. Say I put it like this. Okay, I have H plus and the H plus. Okay, now assume that the first case can be, say, H plus attacking here, this carbon atom, right? Now, obviously, you have to break this bond and put the negative charge on this carbon atom so that the H plus attacks them. Correct. Now, the other case can be, say, it is going to attack this carbon atom, and obviously, the only way is you have to break the bond like this. Right. So they say assume that this is one first pathway, this is the second pathway, right? So we'll see what are the carbocations I'm going to get in both these cases. Obviously, I'm going to get carbocations, no doubt, right? So we'll see what kind of carbocations we're getting, right? So if I take this case, right? So the H plus attacked this carbon atom, and you see this is happening. That is, this carbon atom has lost electron. Correct, right? So I will write it like this. CH3, CH plus CH3. Yes, understood how it came? Exactly same thing what we did last time. H plus attacks here. So obviously this pi bond has to break, give the negative charge to this, and this carbon atom would have had a positive charge. Carbocation. Now tell me, what kind of carbocation is this?
Secondary, sir.
Yes, it's going to be a secondary carbocation because you see that this is attached to two other carbon atoms. The carbon atom having the charge, it attached to two other carbon atoms, so it is secondary. Okay, let me take this pathway, right? So you see the hydrogen atom is attacking this carbon. So obviously the bond should have broken like this. That means this carbon atom will have the negative charge and this carbon atom would have had the positive charge, right? So I would have had something like this: CH3, CH2, CH3. Oh, not CH3, sorry. CH2 plus. Yes, right? So what kind of carbocation is this? What kind of carbocation is this? What kind of carbocation?
Primary, sir.
Primary. You don't have to be confident. It's pretty simple, right? This is the carbon atom having the positive charge. To how many other carbon atoms attached? To only one. Do not think about this. This is not no way connected to the positive charge, right? You just have to look the carbon atoms connected to the positive charge, right? In this case, obviously, you see there are two carbon atoms directly connected to this carbon atom. But in this case, this carbon atom attached to only this carbon. So you are going to get a primary carbocation in this case, right? So again, depending on what is the carbocation formed, right? Depending on what is the carbocation formed. Now I have the Br minus. So now the Br minus, right? Br minus attacks this, right? Br minus attacks here also, right? So what will be the product now? CH3, CH2, CH2, Br. Wherever the positive charge is there, that is where it will go and attack, right? Okay, so now what will be the product here? It will be CH3, right? So CH3, CH, Br, CH3. Right? Now this is what would have been the two products based on what kind of carbocation is formed. Okay, now I told you last time that this is the major product and this is going to be formed in minority. Right? Now what is the reason behind that is because people, there are two carbocations which are possible, secondary and primary, right? And secondary is more stable. Secondary is gonna be secondary I'm talking about especially carbocations, not other things. So secondary carbocations are more stable than primary carbocations, and that's why the H plus. So obviously everything in chemistry goes towards stability, isn't it? The intermediates also are going to be formed based on which is a more stable intermediate. Right. So in the first case you saw, there's a primary carbocation formed. In the second case you saw there can be a secondary carbocation formed. And now I told you that secondary carbocations are more stable than primary carbocations. How? We'll answer the question in the next class. Okay. So now obviously that is why that this, say the second one, this one, right, is the major product. This will be formed in say 80%. And this will be say 20%. This is the minor product. Okay, right? So did you understand, guys? Any questions? Okay, so I think this reaction would have made you understand how important to understand the intermediates as well as the mechanism of the reaction. You don't have to mug up anything, literally nothing, no mugging up. It's all purely logical. Okay, so hope you understood whatever I wanted you to take away, right? So primary, secondary is more, but again, do not mug it up. I'll tell you why this happens also. Correct, right? Fine, guys. I think we'll stop with this for today. Okay, so next class, so now you saw what are the different types of intermediates: primary, secondary, tertiary, carbocation, carbanion, free radicals. Now next class we will be spending time on deciding which is more stable among primary, secondary, tertiary, carbocation, which is more stable, among free radicals, primary, secondary, tertiary, which is more stable. Same thing for your carbanion also, we'll do that, right? And we will also see if I have different carboxylic acids, if I have different alcohols are also a little acidic in nature, right? So how am I going to decide the acidic strengths, right? Which is more acidic, which is less acidic, right? And I told you ammonia is a base, right? So I know amines are also going to be basic: primary amine, secondary amine, tertiary amine. Again, I'm going to see how, what are the different basic strengths. If I give you a primary amine and a secondary amine, or say I give you two different types of amines, which is going to be more basic, which is going to be less basic, all these things we'll see next class. I mean, not exactly next class, we'll take around again some 2-3 classes and we'll complete that. Okay, and after that we'll go for hydrocarbons. Okay, any questions, people? Any questions?
No doubt, sir.
Okay, so I hope everything is clear, right? So I'll stop with this for today, right? So fine. Thank you, guys. Happy Pongal to you again.
Thank you, sir. Wish you the same.
Yeah.
Thank you, sir.
Thank you.